we'll pile on no matter what. Anybody who's missing the class, they can always catch up via the YouTube, the video that I'm going to upload. All right. So MedGAN, we talked about generating completely synthetic data using a GAN architecture, and we briefly covered the architecture first, but let's just take a look at them again in case we've already forgotten the details. So it's the difference between the basic GAN architecture and MedGAN is that, first of all, we have everything. So except for this part, it's just that there's discriminator and that there's a generator, D and G, and the generator accepts a random noise from normal distribution or uniform distribution. So Z is total random noise, and then G, accepting that, will have to generate a realistic sample. And then if you forget about this part, so if you forget about the dotted line, the dotted box here, it'll just be the generated sample from G will go into D, the discriminator, and the discriminator, accepting either the real data from X or the fake data from G, will have to decide whether the given sample is real or fake. So that much is exactly the same. The difference is that since using MedGAN, what we want to generate is not an image, it's a synthetic record. It's a tabular data where each row corresponds to a single sample or a patient, for example, a patient, and each column would correspond to a specific feature. So if we're generating, okay, let me just, so as I said, so if we are generating a counting table, for example, each feature vector, each column corresponds to a specific, for example, diagnosis code, and the value in each column corresponds to how many times each patient received the diagnosis code. For example, like if we have 10 columns where each column is like cough, fever, cancer, diabetes, hypertension, heart failure, such and such, and then the number of times that each patient received each diagnosis code would be a counting vector. If what we're generating is a binary tabular data, then it simply indicates whether the patient has ever received each diagnosis. So one being this patient has received this diagnosis, and 0 meaning that the patient has never received the diagnosis. And we can expand this notion to include both medications and procedures as well, or even lab codes. So as long as we're generating counting counts or binary values, we can extend this. So that is the difference between generating images and tabular counting vectors, counting data or binary data, is that the values must be discrete. So that is different. That is the difference between this, the original GAN, the image generator, and this MedGAN, which is tabular data generator. So that is why we have a autoencoder pre-trained. So we have given an X real data, we have an autoencoder. We are pre-training an autoencoder separately. So this process has nothing to do with GAN training. So there's a simply encoder and decoder. So encoder compresses the real data, and then the decoder will decompress it. And once we've trained the autoencoder, then we just throw away the encoder part and we just take the decoder only. So we take the decoder and then we put a decoder on top of the generator. So now that the generator can only generate the compressed version of realistic electronic health records. So, and so Z is totally random. GZ will generate a meaningful but yet continuous representation of a record of a single electronic health record. And then given that meaningful continuous representation, a decoder will decode that into a count value or a binary value. So it's a converter. So once the decoder converts the GZ into decoder GZ, then the discriminator will accept either this or the actual tabular data, and then have to decide whether it is real or fake. So that is why we have an autoencoder in here. And yeah, discriminator is exactly the same. And as I said before, generator, we design the generator to be a bit more powerful than the discriminator, because as well known, the job of discriminator is so much easier than actually the job of generator, which is to fool the discriminator. So generating a realistic sample is way harder, way more difficult than just simply distinguishing between real and fake sample, at least in the first iterations of the training phase. Because in the early training rounds, the generated samples will be so fake, so easy to tell. So the whole process will be dominated by the discriminator. So we don't want that. We want to have a balance between the discriminator and generator. So that is why we make the generator a bit more powerful than discriminator. So we put a batch norm, and we also add a skip connection. So that and then we put several blocks in that. But for discriminator, no such thing. So for discriminator, there's no batch norm, there's no residual connections or anything. It's just a simple neural network. Right, given that architecture, so we need to talk about the mini-batch averaging first. So it is extremely easy for GAN to fall into, or for the generator to fall into something called mode collapse. So which I hope that everybody's already familiar with. So mode collapse is, simply put, mode collapse is just generator generating only a one or very small number of unique samples to fool the discriminator, because the loss function of the objective in the GAN for the discriminator is simply to distinguish real and fake samples as accurately as possible, and the objective of the generator is to simply fool the discriminator. There's no term, there is no device that encourages the generator to generate a variety of samples. As long as it can fool the discriminator, it's all good. So it's pretty tempting for the generator to generate only a small number of, or maybe even one realistic sample, and just use that always to fool the discriminator. So that is what is called a mode collapse. So the same thing, the mode collapse can happen in the original GAN, or the same could occur in the MedGAN as well. So the MedGAN could learn to generate a single tabular single row in the entire table, just filled with the same value for all the rows, which can simply which can fool the discriminator. So it can easily happen. So in order to prevent that, we use some technique called mini-batch averaging. And this mini-batch averaging it's a general technique. It can be used for generating any tabular data, not just electronic health records, but just any tabular data. You can use mini-batch averaging. So yeah, as it said here, can be used for any discrete variable generation. Does not require additional parameters. So this is the good thing as well. So this doesn't require another neural networks to help the generator avoid falling into mode collapse or anything. It's just a zero cost technique. And essentially what we do is to provide the mean of the current mini batch to the discriminator. So which means that if we're generating a binary variable, if we're generating tabular data filled with binary variables, for example, just filled with zeros or ones all the way, then simply providing the mean of the current mini batch discriminator. This means that what we're doing is simply generating a maximum, like we're providing a Bernoulli success probability of each dimension to the discriminator, because simply taking the average of each column for across all the samples in this current mini batch is just maximum likelihood estimation of the Bernoulli success probability of each dimension K, each dimension. So each medical code, each diagnosis code, each medication code, each procedure code is just whether or not each code or each column would occur or not. And if we are generating a tabular data filled with count variables, then what we're doing with mini-batch averaging is to provide to the discriminator a maximum likelihood estimation of binomial distribution mean, which is NPK of each dimension K. So which is the number of trials, or just number of an event happening, for each column. So the number of times the patient would receive a specific diagnosis code, or specific medication code, or specific procedure code. So graphically speaking, we'll just take a look at the binary variable case as an example. So let's say that this is our real mini batch of real samples. So there's it's filled with let's say this just 8 dimensions. So there are 8 medical codes, and so we're generating a tabular data filled with 8 medical codes. And for example, the first dimension could be whether or not a hypertension was diagnosed for this particular patient or record. And the second dimension could be heart failure. Third dimension could correspond to diabetes and kidney failure, yada yada yada. Cough fever, cough fever, whatever, pneumonia, so on and so forth. And obviously, each record would have different values for each column. So, for example, this patient did receive. So first of all, we're not generating a sequence of visits. We're actually generating a aggregate visit statistics. So, for example, over the past 1 year, whether this patient has received a hypertension diagnosis or not. For this patient, the patient did receive hypertension. For this patient, this patient did not receive hypertension, but this patient did receive heart failure, and so on and so forth. So the combination value here, values would be different for each patient. This patient, or actually we're saying the record. So this record, they have all different values. So if we take a mean, or if we average this mini batch, let's say that there are, I don't know, n number of samples in this mini batch, 1,000 64 or 128, whatever, and we take an average across each dimension, then we can hypothetically we could get a value like this. So 0.13, 0.13, 0.2, 0.11, 0.17, and so what is this? What does this vector mean? This vector represents a occurrence probability of each dimension, or each disease in this case, occurrence probability of each disease throughout this mini batch. And since if the mini batch is large enough, then you can say that this is actually a estimation or approximation of the occurrence probability of each diagnosis code for the entire data, right? Because if we randomly sample, if we randomly construct the mini batch using samples from the actual training data, identically and independently, then this is a estimation of the entire data set. So you can say that with a large enough randomly sampled mini batch, this represents a occurrence probability of hypertension. For example, there is a 13% hypertension occurrence probability in this data set, and there is 2%, not 2%, there is a 20% occurrence probability of heart failure in this data set, and so on and so forth. So this is what happens when you take an average across the entire mini batch filled with real samples. Let's say that there is a generator that generates a very few number of unique samples, which means that the generator has fallen into a mode collapse. So the generator will generate, for example, samples like this. So there's first sample, there's no problem. Second sample has exactly the same value as the first sample. So for this first record, hypertension was received and kidney failure was diagnosed. but all the other disease codes were not. Second record is exactly the same. Hypertension and kidney failure 1, all the others 0. The third example, hypertension and kidney failure both 1, and maybe for the seventh disease this was also 1, but at least this and this is still the same. So the hypertension and kidney failure is all 1 because maybe this is the easiest combination, like hypertension being 1, kidney failure being 1, all the others being 0. Maybe this is the easiest combination to fool the discriminator. So it's just the generators generating the same sample all over again with very small noise added occasionally. So this is the case when this is hypothetical case filled with hypothetical mini batch filled with samples generated from a generator fallen into a mode collapse. And if we take a average of this mini batch across for each dimension, then we would get a value like we would get a vector like this. So since since potentially hypertension is always 1 with very small number of exceptions, and kidney failure also being always 1 with very small number of exceptions, and all the other diseases being all zeros, again with a very small number of exceptions, we would get a vector like this. So 95% chance of hypertension occurring, 91% chance of kidney failure occurring, and almost near zero occurrence probability for all the other dimensions. So it is binary. It is dichotomous. It's either 1 or 0. So compared to this average vector, average from the realistic samples, a mini batch of real samples, and this average vector averaged for a mini batch filled with fake samples with falling into mode collapse. It is definitely different. See here and here. So there is quite a large variety or diversity in the values here, but it's either 1 or 0 here. So we can use this insight if the mode collapse. So this insight only I guess this could go with the images as well. I've not really tried this technique with images, but at least for tabular data filled with seemingly independent columns, because we do not explicitly inject any domain knowledge here. We just simply treat each column or each disease as separate features. I mean, obviously there would be some correlation between, for example, like diabetes would diabetes is likely to co-occur with hypertension, for example, if we are being realistic here. But at least when we are designing the model or designing a data set, we don't really care about correlation or anything. We hope that the model would learn the underlying correlation or even higher order moments. We hope that the model would learn such information, but at least when we're training the model, we don't really inject that kind of knowledge. So in that case, we can simply use in those cases where we treat each column or each feature as independent, as seemingly independent features. This technique is a very well fitted. It's a very nice technique to be used for that kind of data set. So what we do is we concatenate the mini batch average. So we call this the mini batch average. So we concatenate the mini batch average with the input to the discriminator. So what we're doing is we are providing this along with the samples to the discriminator. So we simply we copy paste this we concatenate this with the first sample here like this, and then the second sample and the third sample. So we are simply copy pasting this mini batch average to all the samples in our mini batch. Same goes with here. We copy paste this to the first sample, concatenate it. We concatenate this to the second sample, the third sample, all the way to the last sample in the mini batch. So the dimensionality, the size of dimensions of the input to the discriminator has doubled, because before it was 8 dimensions, but now we're concatenating extra 8 dimensions, which is mini-batch averaging, to each sample. So if before, if the size of the mini-batch was 3 by 8 before, then it would now be 3 by 16. So real input is concatenated with the mini-batch average of real input. Fake input is concatenated with the mini-batch average of fake input, obviously. So if the generator has fallen into mode collapse, then it is extremely easy for the discriminators to distinguish between real and fake samples, because real samples would come with a real mini-batch averaging, which has a variety of diverse set of values. For fake samples that fall into mode collapse would come with a mini-batch average that looks like this. So immediately the discriminator will extremely easy for the discriminator to distinguish between samples samples concatenated with this mini-batch average or samples with concatenated with this average. Like, this is so fake, and this is obviously not. So it is made, but by providing this mini-batch averaging to the discriminator, it is making the job of generator a lot more harder than before, because in order for generator to generate samples to pass the discriminator, it must not fall into mode collapse. It must, so as seen here, the generator must avoid mode collapse to fool the discriminator. So because if it has fallen into mode collapse, it will generate samples that averages into this kind of vector, which makes the job of the discriminator extremely easy. So it's just simply making the job of the generator harder than before, so that it cannot cheat to fool the discriminator. So right. So far, any question with the mini-batch averaging? Nope. If you think about it, you can easily extend the mini-batch averaging technique to incorporate higher order moments. So mean or the average. So what we're doing is simply taking the mean of each dimension and providing that as a extra information. And mean or the average is the first order moment. And if you think about second order moment, which is variance, which corresponds, it's not exactly variance, but which corresponds to variance or standard deviation. I'm sorry. So which is actually no. Yes. We can take a variance. Let me see. Actually, no. I'm sorry. Forget about what I said. I was going to extend this to incorporate correlation, not variance. But I guess you can actually incorporate, add variance information as well. But let's forget about the first. So what I'm trying to say is I said that there must be a correlation between each feature, seemingly independent features. For example, as I said, maybe hypertension co-occurs with diabetes really often, and maybe heart failure also co-occurs with hypertension often, but maybe heart failure and fever doesn't co-occur. So there's like a correlational information between a pair of features. So we can actually incorporate that into, we can actually calculate that and then add that information to the discriminator as well. So this is a single feature information, and we can have a pair of information drawn from a pair of features. So we can have hypertension and hypertension. Oh, I see. So yeah. So the correlation between hypertension and hypertension is actually the variance of hypertension. We can add that to here, and then correlation, the co-occurrence between hypertension and heart failure can be added here, and then correlation between hypertension and diabetes can be added here. So we can, if we do this for all pairs of features, then we are actually adding extra 64 dimension features. So if we're simply adding or concatenating averages or average values, then we're adding 8-dimensional information. like if we concatenate the mini-batch averaging, we're concatenating 8 extra dimensions of information. But if we're concatenating correlation information into the if we want to provide correlation information as well to the discriminator, then we need 64 extra dimensions, because correlation requires a pair of features or pair of columns. So there are 8 columns, so it means that there can be 64 dimensions of correlation information. So in that case, then we are providing 8 plus 8 plus 64 dimensional information into the discriminator. So now the generator has to even consider not only the actual values, but also the average values and also the correlational values as well. So it makes the job of generator that much harder. So generator has to generate samples that respects not only individual values, but it must respect the average value of the features and also the correlation information of the pair of features as well. So it must satisfy all those aspects: the individual values, the average values, and the correlation values. So and you can keep doing that again and again, you know. Again, so just making the job of the generator harder and harder and harder, but it will also make the output. It'll also make the output values that much more realistic. So that is the power of mini-batch averaging. You can just expand this to incorporate higher order information and even higher order. You know. So this MedGAN was applied to 3 separate data sets. And this is large, medium, and small. You can basically say that it's a large, medium, and small. And the largest one includes 260,000. I'm sorry, 260,000 unique patient records, and it is filled with 615 feature vectors. So the dimensionality is 615. Mimic 3 consists of about 46,000 patient records, and we use 1,000 medical 1,000 medical codes or 1,000 feature vectors. So what we did with in raw data, there would be, if we're counting only the diagnosis code, there could be more than 10,000 diagnosis codes, because we're using ICD-9 5-digit diagnosis code. But what we're doing here is we're aggregating that into higher order or higher level categories. So that is why we have only 615 here, 1,000 and 569 here. So Sutter-PAMF is the original data set. Sutter-HF is actually a subset of the Sutter-PAMF data set, where we only extract patient records that is suitable for training a heart failure discriminator, heart failure classifier or heart failure predictor. So, but the semantics is not really important. It's just that what's important here is that this is a this is a superset of this data set. I think there was a question. When the generator makes a sample, how a quantized single output 0, 1 is generated? I think the decoder makes fractional values for loss function. That is a very good point. So the decoder, even with the pre-trained decoder, pre-trained autoencoder, even with the pre-trained decoder of the autoencoder, even with this, the generated value would still be continuous. So we just simply round it up to nearest integer. So that is basically so the output of this here. So the value entering into the discriminator will be rounded up to the nearest integer. And surprisingly, it works pretty well. But if you want to be really accurate about generating a discrete variable, you can use a specific a distribution, for example, like a geometric distribution or something like that, or binomial distribution. But here we simply use the output of a neural network and round it up to the nearest integer. Right. So so these are the baselines. Actually, no, this is not exactly. This is like this is kind of like an ablation study. So we start from the original GAN, and then we arrive at MedGAN with additional techniques added at each step. So there's original GAN, and then GAN P is the original GAN plugged in with the pre-trained autoencoder. So this original GAN with only this added to the generator. And GAN PD is a GAN P plus a mini-batch discrimination, which was a very early technique proposed by people from I forgot, people from DeepMind or OpenAI, I'm not sure. So they propose a technique called mini-batch discrimination, which they claimed that it helped the GAN avoid avoid mode collapse for image generation. But we're not generating image, we're generating tabular data. So, but we're just trying it out as a like a baseline. And the GAN PA is GAN P plus mini-batch averaging, and MedGAN is GAN PA plus giving more power to the generator. So residual connection, batch norm, adding these into the generator. The other models are, these are the baselines for actual comparison between the baselines. So the stupidest example could be random noise. So we start with binary values. So tabular data filled with binary values, 0 or 1. So simply random noise is just flipping 0 to 1 with probability 0. So this is just a perturbation. Given a real sample, we simply we just reverse the value with probability 0.1. So this is simply perturbing or injecting noise into the real data, which can be seen as a legitimate way to de-identify real data. Independent sampling is sampling value of each dimension or each medical code or diagnosis code independently based on the statistics of training set. So you count, you simply estimate, or you simply come up with the average or Bernoulli occurrence probability for each dimension separately, not together, separately, and then sample each dimension independently as well. So at least for each dimension, the generated sample from this technique would observe, would respect the per dimension-wise occurrence probability, but it wouldn't respect any of the correlation information between a pair of dimensions or pair of features. Then we have stacked restricted Boltzmann machine and a variational autoencoder. And what we do is first we perform we do two things for quantitative evaluation. So one is dimension-wise probability. So this is just basic sanity check. We just look at each dimension separately and see if the occurrence probability of each dimension is the same as the occurrence probability. I mean, we take using all these models here and here and here, we generate bunch of fake samples. We generate like the same number of fake samples as the number of training samples, and then we count for each. We evaluate each dimension to see if the occurrence probability, since we're generating binary value, we see if the occurrence probability of each dimension is the same as the occurrence probability estimated from the real samples. So there's occurrence probability estimated from the fake samples and occurrence probability estimated from the real samples. And if the two are exactly the same, then at least we can say that the fake sample, the fake generators, they at least respect the per dimension or dimension-wise occurrence probability. So this is a basic sanity check. And the experiments were conducted on Sutter PAMP, the largest set of studies. So here, the x-axis is the occurrence probability. So each dot corresponds to a single feature or single column of the generated of samples. So here there will be 615 dots because Sutter PAMP has 650 unique codes. So we would see a 615 number of dots here, although we can count it. And then x-axis is the occurrence probability estimated for each dimension from the fake samples, and y-axis is the occurrence probability of each dot estimated or calculated from the real samples. So theoretically, if the occurrence probability estimated from both fake and real samples are exactly the same, then all the dots should lie on the diagonal line, right? So a perfect diagonal line would be, means that at least in this dimensionwise probability evaluation, at least the fake samples and fake samples show the exact same dimensional-wise occurrence probability as the real samples. But unfortunately, for real, again, it's nowhere even close. It all falls here underneath the diagonal line. Again, P seems slightly better. So adding the pre-trained autoencoder decoder seems slightly better. Again, PD, which is using a mini-batch discriminator, mini-batch discrimination technique for the which the authors claim to help the image generation, doesn't help, at least does not help with tabular data generation. When we add the mini-batch averaging, it significantly helps. So if you see here from here, there's a lot of quality jump from here to here. And so now a lot, like most of the dots at least are scattered around the diagonal line. And if we add the batch norm and the residual connection to the generator, then now we are here. So it is almost a perfect diagonal line. So the dot here, so dot here is probably the most frequently occurring code, and dot here is the most rarely occurring code. So this could be like hypertension, this could be some genetic disease or something. So this is the ablation study, and if we compare MedGAN with all the other popular or well-known baselines, random noise random noise is slightly skewed because we're injecting random noise to perturb the realistic samples. So it is not exactly on the diagonal line. Independent sampling, on the other end, is perfectly on the diagonal line, and which makes sense because independent sampling is just we're sampling each dimension independently, and this whole evaluation is dimension-wise probability. So it doesn't really care about. So this evaluation scheme doesn't really care about the correlation between the underlying relationship between many a set of code, a set of feature vectors. I mean, set of columns. It just cares about per column statistics. So that is why independent sampling is perfectly lying on the diagonal line. As for stacked restricted Boltzmann machine, or AKA deep belief network, seems to work well. VAE a bit skewed here, but overall working pretty well. MedGAN is the same as here. So this was dimension-wise, independently dimension-wise probability checking. And if you go to, there is another quantitative evaluation. So we did two quantitative evaluation. One was dimension-wise probability. Second is dimension-wise prediction. So this is actually a bit more interesting. So we're assessing how well MedGAN captures the interdimensional relationship. So in order to do that, what we do is we select one dimension, for example, like hypertension or heart failure, or whatever, some specific dimension K as the label, and we use the remaining dimensions as features. And we train a logistic regression classifier. So we have a logistic regression classifier which accepts all the dimension except for the target dimension K. And we train logistic regression classifier 2 times, one with fake samples and one with real samples. So one LR trained by real data, another LR trained by synthetic data. And we test the 2 LR models performance on a held out real data set. So we have a test set of only real samples, and we test the 2 LR classifiers on this held out real data set. And if the performance of the 2 is exactly the same, then it means that the fake samples is capturing the relationship between, capturing the relationship between the features or between the columns appropriately. Because in order to predict a specific dimension K, we need to the model needs to at least the data set needs to capture the relationship between the K and the remaining features. And we use again, we use binary variable with 260K patient records. Question from Pyongyang. So, how to backpropagate gradients and apply gradient descents of round quantized FN? Oh, actually, no. Sorry. When we're training, we don't care. We don't round up. But when we want to, when we want to generate when we want to do this kind of stuff, like the dimensionwise prediction or dimensionwise probability, that is when we round up. But when we're training, we don't round up. I'm sorry for the confusion. So yeah, during training, we just let it go. And then when we actually generate fake samples and we want to use the fake samples for something, for downstream tasks, that is when we round up. All right, so let's see. So here is exactly the same. So the x-axis is the F1 score of logistic regression trained by real data, and there must be 615 dots here. So for example, here, this particular dot, to evaluate this dot here, what we're doing is we select this dimension K, and then we use the remaining, all the other 614 dimensions as the input to the logistic regression. And then we train LR with fake samples, and this is this exit. So we train LR with fake samples, and we train another LR with real samples. And then we calculate the F1 score. That is the evaluation metric of the binary classifier. We use F1 score of LR trained, and we use the F1 score to evaluate the two LRs, one LR trained with fake samples, one LR trained with real samples. So here, this is the F1 score of LR trained by real data, and this. Oh, I was confused. I thought this was synthetic and this was real. I'm sorry. So F1 x-axis is F1 score of LR trained by real data, and y-axis F1 score of LR trained by synthetic data, but all tested against real test samples, held out, unseen test samples. And again, we want the dots to lie on the diagonal line. That is to say that, if the dots perfectly align on the diagonal line, then it means that the fake samples and real fake samples, their statistic, their values somehow capture the underlying relationship between a pair of dimensions appropriately, as well as the real samples. So as you can see, GAN P, again PD doesn't. So see the jump from GAN P to GAN PA. Minibatch averaging helps quite a lot if you see the difference between here and here, and then the residual connection and the batch norm again helps quite a lot. So if you see the jump from here to here, compared to so if you compare this MedGAN with all the other baselines, random noise seems to do pretty well, but the random noise is just, it's a perturbation. It is not synthetic data generation. Independent sampling, IS, actually just crashes all the way. There's almost all the dimensions. It is unpredictable. So the fake samples generated by independent sampling, and you use those fake samples to train a classifier, then it is just not working at all. And this is obviously true because as the name says, literally we're generating samples independently for each column. So there's no way that the fake samples would capture the relationship between a pair of columns or pair of features. DBN and VAE does pretty well, way better than IS, but DBN, VAE falls a little short compared to DBN, and compared to DBN, MedGAN does a little, ever so slightly better. If you look at like this area here, MedGAN is actually a bit more diagonal than DBN, at least in this region. All right, so yeah, we took a look at the two quantitative evaluation, and you can do this for the all other data set, for using Mimic 3, which is 46K patient records, and we're using, so it's a lot smaller data set compared to 260K patient records. We're only using 46K patient records, still binary variables. And we do, again, the two quantitative evaluation, dimension-wise probability and dimension-wise prediction. And you can see that the MedGAN does better than all the other. I guess DBN does quite a good job, actually. And for dimension-wise prediction, MedGAN does slightly better than DBN and VA, but the overall performance is just way more decreased than here. Like a lot of the sample, a lot of dots here, a lot of dots were sticking to the diagonal line, but here, in both here and here, for the Mimic3, where there should be 1,000 dots, because there were 1,000 unique codes, a lot of them are not actually on the diagonal line. A lot of them like fall on the floor here. So probably because we have a way smaller set of records. We only have 46,000 records compared to 260,000 records in the Sutter data set. We can do the same with a count variable with Sutter HF, which is a subset of the entire data set. So we, instead of 260K, we only have 30K, and instead of using binary variable, this is count variable. So it is a lot more difficult than binary variable, and we only have 30K samples to draw the knowledge from. So dimension-wise average count. So it's no longer average occurrence probability because it's no longer binary. We have count. So dimension-wise average count, and we can see that compared to these two, MedGAN does a pretty good job. So this is independent sampling with a kernel density estimator. This is VAE, and VAE somehow shows like a stepping function type of thing. Compared to these two, MedGAN does a pretty good job. And to see if MedGAN is matching the average count, if it's just matching the average count, or if the occurrence histogram is actually observed, we see that we look at 5 most frequently occurring codes like hypertension disorder, lipid metabolism, connective tissue disease, cardiac dysrhythmia, skin disorder. These 5 were the most frequent codes from dataset C, which is sort of HF, the 30K records. And the histogram is that this is the occurrence histogram. So about 2,500 times, only one time, only the essential hypertension occurs only one time. And about the same number of times, essential hypertension occurs 2 times, 3 times, 4 times, 5 times, 6 times, it is gradually decreasing. Disorder lipid metabolism, about this occurs only one time, about for 4,000 cases. Occurs 2 times for about 2,500 cases, so on and so forth. And so this is basically the histogram of the occurrence for five disease codes. And you can see that this is the histogram of real samples, and this is histogram of fake samples, and it is actually matching quite surprisingly well. I guess except for this, the histogram shape is about the same between these two, between these two, and between these two. So it means that when you generate count data with MedGAN, it doesn't simply match the statistics. It actually observes the histogram as well. Question from 현진님, 황현진님. 직관적으로 Dimensionwise Prediction을 했을 때 F1 스코어의 분포가 리얼 데이터 비슷하면 좋은 선택을 만든 것이 이해가 잘 되는데요. 이것이 정확히 무엇을 의미하는? 피처 간의 상관관계를 잘 구현해 선택 데이터를 의미하는 것일까요? 태블릿 데이터를 사용할 태블릿 데이터를 경우 선택 데이터 평가할 때 보통 이 방법을 사용하는지 궁금합니다. 좋은 질문이에요. 그러니까 지금 여기서 한 거는 이 F1 스코어를 한 거는 한 디멘션을 픽한 다음에 나머지 디멘션을 보고 요 디멘션의 occurrence, 그러니까 0, 1 또는 count를 사실 여기까지 보고 얘기하시죠. 다음을 보면은. So in this case, this is dimension-wise prediction, but it's no longer a occurrence probability prediction. It's because we're not using binary variables. So in this case, what we're doing is we train a LR, we train a, actually this shouldn't be a logistic regression. Dimension-wise. I'm sorry, I'm not. So I think this should have been a dimension-wise prediction. It is still dimensionwise prediction, but we're predicting count variables. So it shouldn't be a logistic regression. This should be linear regression. So sorry about that. I guess this is a typo. But we can still actually this is count variable, so it can't be a F1 score. It should be a mean squared error. I'm sorry. I need to look into this. The description of this table says F1 score of logistic regression. It should be MSE of linear regression if we want to do it. If we want to actually predict the count variable. But anyway, so I guess this is a typo. But anyway, compared to independent sampling and VAE, MedGAN does a way better job of predicting the count variable of a specific feature based on all the other features. So, all right. So given that 이제 현진님의 답을 말하자면 지금 하는 거는 그러니까 이제 하나의 그 피처를 픽한 다음에 나머지 피처를 가지고 하나의 피처의 값을 예상할 수 있느냐라는 태스크를 준 다음에 그걸 가지고 이제 F1 스코어가 리얼이랑 페이크의 F1 스코어가 정확하게 다이고널 라인에 얼라인하냐를 가지고 이제 하는 건데 꼭 그걸 할 필요는 없어요. 그냥 이제 이걸 한다는 거는 이제 릴레이션을 잘 배우냐는 건, 릴레이션이 잘 드러나냐 이 데이터에 그걸 이제 확인하기 위한 건데 꼭 그걸 필요는 없이 어떤 다른 태스크를 해도 되거든요, 사실은. 그러니까 예를 들어서 뭘 할 수 있을까요? 지금 이거는 이제 하트웨어 데이터셋이니까 어떤 특정 디시즈를 예측을 해도 되고요. 그러니까 이제 지금 한 피처를 픽해가지고 나머지 피처를 예측하는 게 아니라 어떤 다른 개별 어떤 피처, 그러니까 우리가 이 제너레이트한 피처가 아니라 개별 어떤 레이블이 있을 수 있잖아요. 이 사람의 죽음이라던가 모탈리티라던가 제2번이라던가 우리가 흔히 하는, 아니면 이 사람의 어떤 미래의 어떤 어떤 특정 하트 페일리어를 예측한다든가 하여튼 뭔가 다른 걸 예측할 수 있잖아요. 이제 우리가 제너레이트한 피처 외의 레이블을 이용하는 클래시파이어를 학습을 해가지고 그걸로 똑같이 질 수가 있겠죠. 이제 그거니까 어떤 사망 예측을 한다 그러면은 페이크 데이터로 트레이닝한 사망 예측기와 리얼 데이터로 트레이닝한 사망 예측기가 있고 그 사망 예측기 두 개를 각각 리얼 데이터에 대해서 테스트를 해본 다음에 그 둘이 성능이 비슷하면은 그때도 마찬가지로 이제 어떤 underlying distribution, underlying 이 relation between 어떤 underlying relation between feature가 잘 이제 보존이 됐다라고 주장을 해볼 수 있는 거죠. 그래서 요런 거를 많이 합니다. 이제 타블 데이터의 경우는 이제 이걸 보통 이 train on synthetic and test on real이라고 그래서 TSTR이라고 그래가지고 어떤 클래시파이어를 신테틱 데이터에 학습한 다음에 리얼 데이터에 테스트를 해보고 이제 그게 잘 되는지를 보는 게 바로 하나의 평가 방법 중 하나입니다. 혹시 답이 됐나요? 네, 좋습니다. All right, moving on. So this is a qualitative evaluation. What we did is, for qualitative evaluation, we generated 50 real, we sampled randomly 50 real records, and we generated 50 fake records randomly, and then we provide them to a real doctor, a real physician, human doctor, in a random order. So, and then we ask the human doctor to score a given sample with a score range between 1 and 10. So 1 being like so fake and 10 being real, most realistic. And we generated count variables instead of binary variables because the doctor said it's way more informative to see count variables rather than binary, which is natural. So we generated using, I think we use Sutter, we use Sutter HF. So we used this data set. We use this data set, 30K patient records and count variables, and we generated 50 fake records and mixed them with the real 50 real records and presented them to a human doctor. And the doctor, so this is a box plot. So here, all real records on average received about score 7, and same goes with real fake samples. Interestingly, so fake samples on average received on average score of 7. So it was on average indistinguishable. But there are a few outliers, like here. There are, so this is a one standard, it's a box class. So this box is like one standard deviation, and then I guess this is like two standard deviation. But there are some notable exceptions here. So 1 and 2 dots here, which means that some fake samples, like 2 fake samples out of 50 fake samples, 2 of them received really low score, like score of 2 and score of 1 by the human doctor. And the reason for that was they were so fake or seemingly fake because some sample contained both male related disease and female related disease. So like, for example, like like cancer in uterus and cancer in like, I don't know, cancer in 그러니까 무슨 뭐 고환암, 그 다음에 난소암 이런 것들은 남자 여자한테만 발생할 수 있는 그 질병이잖아요. 근데 그런 게 동시에 발생한다 이런 거죠. 이제 어떤 한 샘플에 남자만 가질 수 있는 코드와 여자만 가질 수 있는 코드가 동시에 발생하면 그거는 당연히 페이크겠죠. So it's that kind of cases where which makes it so easy for human doctors to say this is fake. So that means that the model, the MedGAN model, has not completely captured the relationship between every single pair of codes, or at least higher order relationship between like a set of codes. That is why it is able to generate samples where both male and female codes are present. So making the job of the human doctor evaluator so much easier. And some other cases are lack of suitable medications. So for example, like if a patient has hypertension, then there should be a medication for hypertension, like, you know, like antihypertensive medications. But, you know, the MedGAN just failed to generate those medications. So that it made the doctor to say this must be fake. But then there was the same thing also happened in real data set as well. So it's not particularly the fault of MedGAN, but at least here, this kind of phenomenon, co-occurrence of male-related, female-related codes, this never happens in real data. So, you know, MedGAN is not a perfect generator, at least. So yeah, this was a qualitative evaluation, and so now we are going to privacy consideration. So this was all based on quality. This all, you know, we were all evaluating the quality of the fake samples. Quality meaning that how much statistically meaningful or similar the fake samples are compared to the real samples, both quantitatively and qualitatively. And at least we've covered that to some extent. Both qualitative and quantitative, MedGAN is doing a pretty good job, pretty solid job. Now it's time to take a look at the privacy side of it. So what if MedGAN is simply just, you know, memorizing the real data, real samples, and just spitting them out, just copy pasting them out? If that's the case, then it's probably, you know, there's zero privacy protection here happening. And as I said in the beginning, the motivation for developing or designing MedGAN was to generate samples to synthetic samples to encourage researchers to do research on fake sample on electronic health records without risking privacy, without risking privacy leak, basically. But if MedGAN is simply copy pasting real samples, then there is still a privacy risk. So we cannot, you know, we cannot publicly share the fake samples generated by MedGAN, because, you know, it's just a copy paste machine. So we're just evaluating fake samples in that aspect. So we do two privacy attacks. One is membership inference attack, and another is called attribute disclosure attack. So membership inference is actually a pretty straightforward concept. So the attacker has complete knowledge of a patient group P. So for example, attacker knows the complete record of John, Mary, you know, Stuart, and Sarah, and, you know, like some number of people. So attacker already has a complete knowledge of some number of people, and the attacker observes the synthetic data set from MedGAN. So MedGAN is a synthetic data generator. So for example, let's say that some researcher or some company generated like millions of synthetic data set synthetic records using MedGAN, and then they released it publicly. So now the attacker has complete access to synthetic data set from MedGAN, and the attacker also has complete knowledge of a small number of patient groups. And now what the attacker can do or tries to do is to identify if anyone from P that the attacker has complete knowledge of is in the training set. So by looking at the synthetic records generated from MedGAN, the attacker wants to identify or infer if a certain person, if a certain record was used to train MedGAN by looking at the synthetic data set. So it's like an indirect inference. And if so, then if the attacker can know, then there's definitely a privacy leak. So that is membership inference attack. And another, a bit more interesting attack is attribute disclosure. See, so here the attacker has partial knowledge of patient X. So for example, like attacker knows, attacker is a friend of John, and the attacker knows that John has had a heart failure in the past year, in the past year, and the attacker knows that John also had hypertension in the past year. So, but the attacker does not know that John had, if John had any other diagnoses or medications. So the attacker doesn't know that if John was diagnosed with cancer or was diagnosed with pneumonia, doesn't know. But at least that attacker knows that John was diagnosed with heart failure and hypertension, and that's it. So given that partial knowledge, the attacker has access to the entire synthetic data set generated from MedGAN, and then attacker wants to learn new knowledge of the patient X, John, such as diagnosis or medication. So given the knowledge that John has had hypertension and heart failure in the past, and looking at the bunch of millions of records, millions of synthetic records generated from MedGAN, the attacker wants to learn if John had received cancer or was prescribed with anti-cancer medication, something like that. So in this case, if the attacker is, an insurance company, then this could be a very valuable information. So if John has had a, like cancer in the past, then as a insurance company, the insurance company would like to charge a higher premium to John. So this kind of knowledge, this attribute disclosure, or if you are, I don't know, if you're like a really like a perpetrator, like a criminal, then after learning, using a partial knowledge of someone, and then gaining extra knowledge of that person by looking into the synthetic data, then maybe you can threaten, blackmail the person to, like such as like, if you don't give me money, I'm going to release this information to insurance company, or if you don't give me money, I have learned that you have this sexually transmitted disease like in last year, and if you don't give me money, I'm going to release this information to your job so that you're humiliated and you're going to get fired, something like this basically. So this attribute disclosure is a way more interesting scenario compared to just simple membership inference attack. Because at least in my estimation, simply knowing that a person that or a medical record of a person that was used to train a synthetic data generator. I'm not sure what kind of how you can exploit that information for monetary gain. 그러니까 단순히 내가 아는 사람의 메디컬 레코드가 어떤 이 모델을 학습하는 데 있어서 끼어들어갔다라는 거를 아는 게 어떻게 이게 나한테 이득이 되는지를 잘은 모르겠거든요, 사실. 혹시 아는 분 계신가요? 왜 그게 이제 뭐 안다기보다는 뭐 좋은 아이디어가 있나? 이걸 어떻게 이용해서 뭐 협박을 하거나 아니면 뭔가를 어떤 이득을 취할 수 있는 구석이 있는지 이걸 아는 순간 어떤 아이디어가 있으신 분 있을까요? Any idea who has creative idea, like creative way to exploit this knowledge for my personal gain? This is pretty clear. Like, as I said, attribute disclosure is pretty clear. You can gain extra knowledge and then start blackmailing. But if you already have a complete knowledge of a patient group, so you already know that John was diagnosed with cancer, John was diagnosed with sexually transmitted disease, and then you can use that information anyway. So what is the point of knowing that John's record was inside, John was, included in the training set to train a machine learning model? What is the point of that? Unless you can say that, I guess you can blackmail a researcher or a company that trained MedGAN. Like, I know that you use my friend John's medical record to train MedGAN. So there is a privacy leak, something like that. Unless, like, besides that, I'm not sure what we can do with this knowledge. But it is still a privacy leak, because we know that that a certain patient record was, inside, was used to train MedGAN. So at least we know that. So we know that a certain person was provided their medical record to a company or not. But aside from that, I'm not really sure what we can do with that. All right. So unless any of the participants today have a great idea how to exploit that, I'm just going to move on. I guess we're running actually out of time, so we have to continue this next week as well. Yeah, extending this, I would also like to talk about differential privacy as well, but we're running out of time. So next Tuesday, we can talk about differential privacy along with federated learning, because all of them are actually, intertwined. Because the reason that we're using federated learning is to prevent from privacy leak happening. So like differential privacy, federated learning, then multi-party communication. There are a lot of methods to prevent privacy risk, or to encourage privacy protection. So this is all like interrelated. So we're going to talk about that next Tuesday. 변영진님, 이 사람이 저것이 데이터를 제공했구나, 저 병원에 갔구나라든가 있을까요? 그것도 가능하겠네요. 그러니까 내가 이 사람이 어떠한 병을 겪었고 어떠한 약을 먹었다라는 건 이미 알고 있지만, 이 모델이 어떤 회사나 어떤 병원이 릴리스를 했다고 치면은 우리가 이 사람이 이 사람이 자기의 데이터를 그 병원 또는 그 병원에 제공했구나 라는 건 알 수가 있겠죠. 그거를 이용해서 뭔가 그러니까 그거 자체가 이미 이제 개인정보가 유출된 건 맞거든요. 이 사람이 저 병원에 갔다는 사실을 아는 것 자체가 이제 뭐 아는 거긴 한데, 그거를 어떻게 이제 뭔가 협박을 하던가 뭔가를 이용해서 이제 돈을 뭔가 나에게 내 개인이 이득을 취할 수 있는 거가 있는지가 명확하지 않은 것 같아요. 하지만 이 멤버십 인프런스 어택은 이제 굉장히 뭐 자주들 하는 겁니다. 그냥 이제 내가 어떤 뭐 프라이버시 프로텍팅 알고리즘을 개발했다거나 뭐 이런 걸 할 때 이제 멤버십 인프런스는 기본적으로 합니다. 네, 요걸 할 수 있다 없다가 이제 적어도 어떤 기본 어떤 세니티 책 같은 거죠. 내가 만든 이 privacy preserving 알고리즘은 요 멤버십 인프런스 어택이 불가능하다. 뭐 이런 것들이 이제 뭐 증명하는 데 사용하긴 하죠. All right, so the setup of membership inference attack is like this. So we select R number of patients from two separate real data sets. So that means that assume the attacker has complete knowledge of two R patients. For example, like R could be 100, R could be 1,000, R could be 10. It doesn't really matter. This is a hyperparameter. So let's just say that R is 10 for now. So we select 20 patients. So 10 from a real data set A and 10 from another data set, non-overlapping data set B, so 10 from each. So the attacker has complete knowledge of 20 patients. And for each of 20 patients, we calculate a Hamming distance with all synthetic data, So we have a bunch of synthetic data, like 1 million synthetic data, or whatever. So we have like huge amount of synthetic records. And for each of the 20 records, we calculate Hamming distance with each and every synthetic record. And the premise is that the synthetic data are generated based on the real data set A. So only A was used to train the synthetic data generator. So that are generated based on real data set A. And a match or a mismatch based on Hamming distance. So Hamming distance is basically, if you have a 0, 1, a vector is filled with 0, 1, and the Hamming distance is how many columns match or how many columns mismatch. So if you have a 10-dimensional vector filled with 0 and 1, and if you have 2 samples exactly matching all the 0s and 1, then the Hamming distance is 0. If you have 2 samples with all the zeros filled with 0s and 1, and if the 2 samples differ by only 1 dimension, then the Hamming distance is 1, and so on and so forth. So a match or mismatch based on Hamming distance is either true positive. So given your 20 patients, you calculate Hamming distance with all synthetic data that was generated from A. But your 20 patients come from A and B. So true positive is that when the matching patient comes from A, so among your 10 patients from A is matching. So one of your 10 patients from A is matching with a synthetic record that was generated based on A, then that is a true positive. False positive is that when one of 10 patient records from B is a completely matching record with fake synthetic data that was generated from A, then it is fake. It's a false positive because they should not be matched, because only matching cases should occur between A and synthetic samples. But if a matching sample occurs between B and a synthetic sample, then that's a false positive because the synthetic data was generated based on A, not B. So that's a false positive. True negative is mismatching patient comes from B. So all your 10 samples, all the samples that attacker completely has knowledge of, the 10 samples coming from B is not matching with any of the synthetic data, then it's a true negative because it should not match. False negative is when the mismatching patient comes from A, because A synthetic data, because the 10 records coming from A should actually be matched with all 10 samples. All 10 samples coming from A should be matched with at least 10, be matched with the synthetic data. But if it's not, then it's false negative. So there are 4 cases. And then what we do is we calculate mean and sensitivity. We calculate mean sensitivity and mean precision while varying the R, which is the hyperparameter, the amount of known patient to the attacker, and the Hamming threshold. So Hamming threshold is like, if 2 samples are 1 Hamming distance away, then we treat that as a match. Or sometimes we treat Hamming distance of 2 to be a match, something like that. So we can adjust the Hamming distance threshold to define whether something is a match or a mismatch. And we experiment this. The experiment was conducted on MIMIC3, the binary variable case. So far, hopefully, this setup is clear to everybody. And so this is the result. So what we as I said, we are using R as hyperparameter. So we're increasing the number R, and here as well. And this is sensitivity. So this is recall, and both recall and precision can be calculated based on these 4 values. So the recall is, what is recall? Recall is it's the predicted outcome the denominator being the predicted outcome, and the numerator being the real numerator being the actual positive values. So it would be mismatch comes. I'm getting confused here. So it's the number of true samples divided by true positive plus false positive. So it would be true positive plus true negative. Is it? No, sorry. True positive plus false negative divided by true positive plus false positive. Is that correct? I'm going to write it right in the chat box here. So sensitivity is equals true positive plus false positive, true positive plus false negative divided by true positive plus false positive. Is this correct? So it's the actual number of positive samples divided by the predicted number of positive samples. And precision is true positive divided by true positive plus false positive. How much we made the correct prediction. True positive, true negative. Oh, actually, it should be true, false positive, true negative. I'm sorry, I think this is, yeah, the sensitivity should be true positive plus false negative. True positive I'm sorry. Oh, okay. Thanks for the copy pasting. Okay, so sensitivity is true positive divided by true positive plus false negative. Let me see, true positive, false negative. Oh, that is correct. I'm sorry. Yeah, it should be. So the denominator should be all number of positive samples, and the numerator should be the correctly predicted positive sample. So for sensitivity, specificity is not precision. Precision and specificity is a different thing. So 1 minus specificity is actually false alarm. So precision, I guess precision is then precision is, yeah, it's TP divided by TP plus, yeah, it's the number of true positive divided by the positively predicted values. So that is precision. So here, what is happening here is that as we increase the number of patients known to attacker, so here we are increasing the number R, and the line here indicates the different Hamming distance threshold. So Hamming distance threshold being 0 means that only if and only if the fake samples and the fake sample and only if and only if the samples known to the attacker is a complete match with the fake samples, synthetic samples, then it is a match. So that's when Hamming distance 0 means. And Hamming distance of 5 means that if the records known to the patient and the records from the synthetic records are 5 Hamming distance away or less, then it is a match. It's something like that. So sensitivity. So obviously sensitivity is rising. Obviously, sensitivity rising means that, for example, like if Hamming distance being 20 means that you are going to treat as a match between when the records known to the attacker and the records from the synthetic samples are 20 Hamming distance away or less. So in that case, you're getting a lot of matches, like a lot of matches. And if you treat all of them as matches, then obviously your recall, sensitivity is actually recall, your recall is going to rise. But it is invariant to the number of patients known to the attacker. Almost invariant, except for the very small number of R cases, like if when R is like 10 or 5, except for those cases, increasing the value R has no effect to the sensitivity. So doesn't matter whether if we fix the Hamming distance to 0, threshold to 0, it means that if you set the Hamming distance to 0, then knowing 2,000, the attacker knowing 2,000 records and knowing attacker knowing 10,000 records doesn't have the effect to the recall. It doesn't matter. And same goes with precision. Actually, precision is interestingly. For precision, Hamming distance threshold doesn't really matter as long if we start increasing the value R. So it's always 50%, no matter what. Except for cases where R is really small, is if like R is like 5 or 10. So in that, except for those cases, precision is 50%. And for precision being 50% means that what does it mean by the definition? It means that only half of your predictions are correct. Half of your predictions are true positive, actually. So if you say that oh, I have a matching case of 100, then only 50 of them are actual real matches, true positives. All the others will be like false negatives. I mean false positives. So you don't know that which of them. In that case, you don't know which of the 50% are actual real samples, and you don't know which of the other 50% are fake samples. So it's virtually impossible, except for this case, like when the R is like 1 or 2. In that case, precision is pretty high. Precision is like almost 80%. So you have an 80% confidence that the ones that you say that as an attacker, you say that it is a match. There's an 80% chance that it is actual real record. But if you start except for those cases, if you have a lot of knowledge, as you have increasingly larger knowledge of the patient, like a larger patient knowledge, then it's virtually impossible to tell which is fake and which is real. This here is we're actually increasing the number of synthetic patients. So this is to say that if we generate more synthetic samples using MedGAN, does that lead to higher privacy risk? And the answer is no. So when we use 5,000 synthetic samples, and when we use 35,000 synthetic samples, I mean that means that the attacker has access to 5,000 synthetic samples, and the attacker has access to 35,000 synthetic samples. The sensitivity and precision doesn't change. So the only thing that really matters is when the patient knows really small amount of real records. So in that case, yes, it is. There could be some risk, but in all other cases, not so much. And even when the patient, the attacker knows really small number of real records with Hamming distance 0, the sensitivity is at most 20%. So it means that out of all, like if the attacker knows like 10 people, then at most the membership inference attack will tell the attacker that 2 of them only 2 of them can be identified to have been in the training set. So, and you don't know which one. You only know by 80% confidence. So basically, it's really hard to know that. Really hard, unless except for the very specific cases, it's really hard to do a membership inference attack using the synthetic records generated by MedGAN. Yeah, we'll continue with the attribute disclosure next Tuesday. Actually, yeah, we'll just recap this one as well, because I kind of tried to do this within a really small amount of time frame. All right, any question? About the membership inference attack? No? Yeah, this is a pretty straightforward concept. So maybe we can talk more about attribute disclosure next time. All right, thank you guys. I'll see you guys next Tuesday. Bye-bye.